microscopy is, as you know, that it is a big topic. So it is very difficult for me to finish it in 1.5 hour or 2 hours. But I will try my best to do that. So yeah. So if you yeah. So. So I think all of you know about discovery of electrons, and all of you might be aware that de Broglie's theory of duality, wave particle. So let us start from first understanding electrons. So before that, because we are learning microscopy, so microscopy has changed a lot the way it used to be understood. So now microscopy is a combination of microscopy, which is basically looking at the things at a smaller and smaller scale, and also it merges spectroscopy. For example, you can merge Raman spectroscopy, you can merge IR spectroscopy, even UV visible. You can go to a more advanced form of microscopies, for example, near field modes. One I would like to name a few. Scanning near field optical microscopy, where you can see normal optical microscopy, you cannot basically image the objects which are less than half of the wavelength of light visible. If you talk about visible range, so that comes around something around 250 nanometer. So that's a problem with the far field optical microscopy. But when you use near field optical microscopy, so things are much better than what they are. So you can combine all these things actually. And also students are interested in modifying their the objects. For example, you would like to do the synthesis in the microscope. Actually, you would like to do some simple synthesis. For example, suppose you are doing some catalytic reaction. So you would like to observe the catalytic reaction inside the microscope and see the intermediate phases, because that's a problem chemistry students most of the time they face, because some of the information is lost actually, the phases which are there in the intermediate stages. So all those things are possible, and if the chemistry students are interested in looking at the live reactions, so of course they would like to have a control over temperature and pressure, and also they would like to introduce some gases. Of course, you can't put a beaker there. Don't expect to do that. But there are some. I mean, you have to also compromise as a student that okay, I will miniaturize my reaction. I will carry out a small. See, pilots, when we call it like a pilot scale, it is mostly at a larger level, right? At a larger level. Why you can't do it at a smaller level, reverse level, right? Reverse the reverse direction. So you have to. I keep this thought to all of you to consider how this thing can be done. So microscopy is actually extension of our 5 senses that we would like to test and feel, manipulate, create, move things actually. So you would like to move molecules. You would like to arrange them in certain way. So there are so many things you would like to do with the molecules and particles actually. Whether you are an organic chemist or you are a polymer chemist, or you are an inorganic chemist, or a physical chemist, or you are an engineer. So so far I have written. I have got, I think, okay, people who have joined just now. Who are also requested to keep. Putting this reminder in the message box that students who have not shared their attendance, they will share that attendance. Okay, please co-host keep typing in, because some people are joining late. Okay, so let us, thanks co-host all of you. Thanks a lot, it's a great help. So this is the reference material. I would like to just point out one book here, which is sufficient, available in library, William and Carter. You don't need to read tons of books, but this book is very good book actually. And if you're daredevil, then you would like to read other books also. For example, this one, and then this one and that one. So, but it's not required actually, unless you want to become a teacher like me. If anybody among you is planning to do some experiments on live cells, or not live cells basically. You can't do it using this technique. Using atomic force microscopy, you can probe live cells, but here you would like to fix the cells. So those techniques of processing the mammalian cells or microbial cells are there in this book by Bozola and Russell. It's a great book. This is the only book which is required for biologists. Okay, so let us look at one by one. All of you are aware from your school books about the discovery of electrons by J.J. Thomson, and he didn't name electrons as electrons, right? So he just named corpuscles, and then everybody accepted that we can name this negative charge as electron. And don't imagine electron as a spherical ball of a certain mass and like a negative charge. There is nothing spherical in this world. So one electron is made of 3 quarks, right? And which are which has got gluon. So we can approximate that as a sphere, but it is not necessarily basically it's a okay. So after that, von Love and colleague basically they were the first people. They were able to claim that X-rays can form diffraction pattern, and they got the so von Love, and actually it was a teamwork. I will probably go a little bit deeper into that because it's very important. But then only von Love got the Nobel Prize in 1914 for telling the world that X-rays can diffract. But he didn't solve the crystal structure. So first crystal structure solution was given, I think all of you know, by Bragg, father and son. So they solved the crystal structure of copper sulfate, and they gave a simple equation, and lambda is equal to 2d sine theta, and which we still use. So Mosley's contribution is amazing, as per my opinion, that he was able to tell about one technique which chemists they love, because chemists would like to know which element out of periodic table is there in my material. Okay, there are several techniques. You can use AAS, and you can use ICP. You can use many other techniques, but those are broad techniques. Actually, those are not. Those cannot give you information about localized information. For example, those techniques are basically will tell you averaged out information about a large area. That if you want to know that the uniformity, if there is any elemental uniformity in your sample, so of course you would like to do something called basically electron energy loss spectroscopy, or you would like to do X-ray spectroscopy, energy dispersive. Okay, we'll discuss about this EDS. Okay, yes. So Mosley was the first. See, Mendeleev's periodic table, it was a very messy affair. So then Mosley basically put the ordered periodic table in a nice way, what we see, and he was able to relate the X-ray emission from the core level to their atomic number, right? And then came de Broglie's contribution, which is very important. He said, okay, these particles can behave as waves and waves as well as particles. We will see what is the implication of that in a practical electron microscopy, which techniques of electron microscopies are derived by the particle behavior, and which techniques are derived by wave behavior. So these things are a little bit, I will not cover because those are for physicists and engineers, but there are a lot of effort because most of the students are from chemistry background. Though I'm a physicist, so I love to go into details. So basically there was a lot of effort by scientists to make electron lenses. So please know that similar to optical microscopy, where we need better and better lenses, usually those are borosilicate or some other glass material. Here also we need to have lenses. So these lenses are magnetic lenses. Those are basically made, you have to have a magnetic field. So magnetic field is able to drive the electrons the way we want, right? everywhere, any charged particle, whether it is any accelerator, everywhere, this is magnetic field and electric field together. Electric field basically speed it up. It gives it different energy, and magnetic field basically drives it around. It gives it direction actually. Okay, so if you see all these accelerators in Europe, and so those are all in fact all these discovery of what you call it, godlike particle, whatever those were all done by colliding proton beam, highly energetic. Okay, so those were basically you need large magnets actually. So then Davison, German, and Thomson Reed, they proved that okay, electrons can also diffract. So that was a big thing, because that means you can do the electron diffraction similar to the X-ray diffraction. Wow, that's very amazing. So, but we have to then obviously chemistry students would like to ask the question that if I do the X-ray diffraction and if I do electron diffraction, what I'm getting, how can I compare? So those are complex topics which I cannot cover today because it will take longer time. But those are the questions. So Ruska was a young guy in 1931, and he made first EM in 1986. And after that, another related techniques like scanning transmission electron microscopy was developed. Commercialization of EM happened by a German company, okay, Siemens, which is still there in the medical field mostly. Then there were other, I will not go into detail because of lack of time, but you can read that. So right now I would like to highlight one more important thing, that 1986, almost 50 years later, Nobel Prize was given to Ruska together with Biening and Rohrer. These two people developed scanning tunneling microscope, which was at that date and still even today, it's the highest resolution microscope. Believe me, scanning tunneling microscope had the record of giving you highest vertical resolution, and this is still the okay record. So right now, the resolution of electron microscope has gone. I think some students keep on informing me in my class, 0.35 angstrom, right? And what is the diameter of a hydrogen atom? It is 0.5 angstrom. So that means you don't need that much of resolution, because it is enough actually. Okay, and there are other problems also. I mean, that's not the problem that you want to keep on increasing the resolution. That's not. But so, what are the bottlenecks in the resolution? As same terminology which we use in optical, geometric optics, aberration, actually spherical aberration and chromatic aberration. I will not be able to cover that part today because it's a very basic course. So Nobel Prize in Chemistry of 2017 was again stolen from the chemist by biochemists. Actually, these were all biochemists, and this year's Nobel Prize was also picked up not by chemists but by people who are doing biology actually. So last year, material science got the Nobel Prize. In fact, physicists. So the honor of building first Indian transmission electron microscope goes to Professor N. Das Gupta, and he developed it actually at Saha Institute of Nuclear Physics, and it is still kept in a glass enclosure for the safety reasons. And so I will skip all these details unless you have any question. So this equation you have to remember that de Broglie's wavelength, we call it like h over p. H is the Planck constant and m is the electron mass, p is the velocity. So this will be very useful for us because for any microscope we need to know the wavelength of the radiation, whether it is a visible light or anything else. So if we are using electrons, then we want to know the lambda, which is wavelength. of associated with the with the electrons. So electrons, again, as I told you that I asked this question earlier. I would like to answer this question now, that if you use particle behavior of electrons, uh, then those are helpful for you to understand EDAX, which is so dear to chemists actually. And backscatter electrons, again, backscatter electron technique is similar to Rutherford technique. Rutherford used and his group actually, his students use alpha particles, which are positively charged particles. But here we use backscattered electrons actually. Those are elastically scattered. There is no energy loss. This technique is useful for if you want to get elemental analysis again, which chemists would like to have. So this technique EDAX is also useful for elemental analysis, okay, analytical chemistry. And but here the energy resolution is not that good, because chemists are more and more demand, what you call it actually, they're demanding more and more actually, that dil mange more. तो अगर दिल ज्यादा ज्यादा कुछ मांगेगा, बोलेगा दिल बोलेगा नहीं यार मुझे तो ऑक्सीडेशन स्टेट भी चाहिए, आई वांट बैलेंस स्टेट, मैंगनीज +2 है, +3 है, मैंगनीज का पड़ोसी कौन है. So then these techniques are not very good for you. Okay. So then you would like to use yields. Yields can tell you कि कार्बन sp2 hybridized है या फिर sp3 hybridized है. Those details which you can, and also see, you will say that array, I can tell you these details by using XPS, but XPS is actually full of its own problems. One of the major problems is basically those atoms which are sitting only within 1 or 2 nanometer, those are probed. And another thing that it's again a bulk measurement, because the beam which is when you are collecting the photoelectrons, you're collecting from a large area, several microns. Here you can tell about every atom. So you got it. तो यहाँ पे आप हर एटम के बारे में जानकारी कर सकते हो, जैसे एटम लेवल का आप मैपिंग कर सकते हो. समझ में आ गया ना, व्हाट इज द डिफरेंस बिटवीन AS एंड ICP. ये सारे बोलोगे भाई मुझे तो ये भी दे देते हैं, पर उसमें 2-3 ग्राम में आपको कितना आपको ये नहीं मालूम पड़ेगा कि वो एटम कहाँ बैठा था. यहाँ पे आपको मालूम पड़ जाएगा कि दिस एटम का पड़ोसी कौन था, राइट. So for example, now I know that so many students are listening to this class, but I do not know who is sitting where. Okay, how many male, how many female, I can know from the names, but I do not know कि वो कौन से district में है, कौन से गांव में है, कौन सी. Okay, because I don't have that local information. I have a global information. Okay, I know the information about a tree, but I do not know the information about every leaf actually, right. I would like to know the diffraction also. So then if you treat electron by wave, then you can get information about their crystallinity, कि भी कहाँ पे किस order में बैठे हैं, कौन सी growth हुई है. And it is very important for catalytic activity, because all the catalytical activity is dependent on which plane you grow in comparison to other planes. So because you know that some surfaces are more active than other surfaces. Even in the polymer chemistry, you know that crystallization plays a major role in deciding whether the polymer will be hard or soft, or many things are there. Also, you would like to know some phase transition in polymers as a function of temperature. When you make a bottle of Coca-Cola, or you want to make some other toys, so you want toys to be soft, and the cover of the bottle should be hard, and different plastics are different. So next you can go to proteins. You want to know protein crystallography, you want to solve the structure. So those are the objectives of a modern student who is struggling with a complex problem as of today. So you can see here I have simplified this equation that lambda. You can here this equation you can put directly the accelerating voltage. So V is basically the voltage by which you accelerate the electron. So basically in electron microscopy, we call it operating voltage. Operating voltage is mostly in kilo electron volt. Okay, समझ में आ गया ना? In TEM, so it can be 100 kilo electron volt, or it can be 200 kilo electron volt. Sometimes it can be 300 kilo electron volt. It can be any other electron volt, like, you know, I'm just giving you 3 examples out of simplicity. It's not like it can be 101, it can be 222, but we will just, for the simplicity of calculation, would like to consider that. So if you put this voltage in this equation here, so you can calculate the associated lambda. Of course, you know, we are talking about high energy electrons here. This energy is very high. You know, believe me, you know, it's if the entire energy is transferred of electron beam on your skin, so your skin will just become you know, plasma actually. Okay, believe me. So don't ever do that. Okay. So that's the reason that and electron speed becomes larger, you know, more than you know, half of the speed of light. Then you have to invoke the relativistic effect. So then you have relativistic corrections also. And if we calculate accelerating voltage and then we calculate the wavelength, you can see the wavelength is so small actually. Okay, you can see that for example, for 200 kilo electron volt, wavelength is so small, picometer में चला गया, around let's say 3 picometer. अब 3 picometer तो बहुत छोटा हो गया, right? Now now so what will happen that so suppose you so can you please admit the co-host, you know, admit the students? Yes, Asma, please do that. Yeah, I hope co-hosts are not logged out. So anyway, so I told you the resolution is half of this actually. So resolution for an electron microscope working at 200 kilo electron volt will be, resolution will be half of this. For example, 3 picometer divided by 2. 1.5 पिकोमीटर, ये तो बहुत छोटा हो गया यार, बहुत ज्यादा छोटा हो गया. तो अब हमें इतना चाहिए क्या? नहीं चाहिए, इतना छोटा नहीं चाहिए. और इतना मिलता है, इतना रेजोल्यूशन हमें आता है क्या? नहीं आता है. इसका रीजन वही है, एब्रेविएशन, बिकॉज नो इलेक्ट्रॉन, नो माइक्रोस्कोप इज परफेक्ट. So you can see that okay. So this is the summary of Lovey and everything. I will skip it, though it is very interesting story. So Mr. Abe was, you know, Carl Zeiss, you know, the Carl Zeiss company still makes electron microscope. Carl Zeiss makes your मोबाइल का जो लेंस होता है ना, जो आपका कैमरे का लेंस, वो Carl Zeiss का सबसे बेस्ट होता है. पहले सोनी के जो मिलते थे मोबाइल, they used to put Carl Zeiss lens. Even if you now if you buy a Samsung mobile, Samsung generally put Carl Zeiss lens, which are considered the best lenses. You know, unless you're buying some Chinese mobile, so you may not get Carl Zeiss lens. That's the reason that Samsung mobiles are sometimes expensive, because the hardware is way apart. You know, you can put some cheap plastic lenses and then you can you can enhance your selfie by software rather than actually hardware. You know, hardware is very cheap. That's how. So there is a lot of physics and chemistry involved and engineering involved. So Abe was Ernest Abe was a partner of this Carl Zeiss actually, जिसके नाम से company थी. So he said that he was very pessimistic that time. बोल रहा कि optical microscope 200 nanometer से 250 nanometer से resolution, you cannot see the word below this, but you know that it is false. So so this guy Otto Schott and Carl Zeiss, they developed a lot of interesting microscopes, and he is still his equation we use. So okay, so he was right actually at that time, that because we have the wavelength constraint, so there was no he gave the equation which we are still using. But उस जमाने में basically we didn't have any radiation which was because X-ray बहुत बाद में आई है ना, X-rays came much later, and then that time even today we don't have X-ray microscope because it's not possible to make X-ray, optics for X-ray. You cannot make lenses. So converging, diverging X-rays, it's a difficult task. Okay, so then this is photograph of Ernest Ruska, and so this is the Nobel Prize. Happy people partying. So magnification is basically, that it is the size of the feature size in the image plane, and ratio of image plane and the object plane. Okay, see this. Okay, so this ratio of this actually. Okay, suppose you take a point and then you magnify it. Okay, so this is the image plane actually, right? This is the image plane and this is the object plane. So you are trying to magnify this. So the ratio of this and this. But resolution is very different altogether. Okay, so you can have an empty magnification without any information. So how do you understand the resolution? Resolution is understood by this. You can see that this is the so these 2 points are considered resolved. These 2 points are considered resolved, and this point is not considered resolved. Why? The condition is that यहाँ पे मैंने कहीं लिख दिया है, that the these are basically diffraction patterns of each light source. So you can see there are 2 patterns. So this is central maximum, and right, and this is the first maximum, and this is the first minimum here, somewhere here. So if you see that when the distance should be if the distance between 2 pixels is less than the distance between the central maximum and the first minimum of the second source, then you cannot resolve. So that's why you cannot resolve it here. So if the distance is larger than this, you can see that this is larger than this, so you can consider it resolved. So I'm erasing this and you can see it clearly. You zoom it here. Okay, I will find, please let me, so you zoom this on your screen. I don't know whether you can zoom this. Okay, so you zoom this if you are using mobile or something, then you will be able to see clearly what I'm talking about. And let me move to the and so human eye resolution is very not very good. You know that it's around 200 micron. Okay, and that's why you cannot see COVID virus on surfaces. Otherwise, you will be seeing this and getting scared also all the time. So and you will see different world if your eyes were much better. So ignorance is the bliss sometimes. Light microscope, as I told you, that it cannot go beyond 200 nanometer, going by the Abbe and Rayleigh limit. Scanning electron microscope, SEM stands for, S stands for scanning, E for electron, M for microscopy. So SEM we will discuss today at the end. It's a different technique based on electron microscopy again. So if some students have taken class in the previous semester, because of this new education policy, or I don't know what reason, ACISI has cancelled my class and many other classes. I think all of you are aware of that. So you will not have luxury of learning this in deep. So if you are interested in taking a semester-long course, unofficially, it unofficially means I'll be teaching with the same energy, but you don't need to pass any exam unless you want to do that, a fake exam. Okay, I can conduct a fake exam, but it's not required. My students who attended last classes, they know that I love teaching, but I hate taking exams. So, but you can write email to me if you are really very serious, because you know that it is a big time commitment from my side. So I can teach you on online platforms if you are really interested. Otherwise, Okay, last semester students were very serious, very nice quality students I get each semester, and they did very good. And so we'll see. Okay, so so this is the Abbe criteria. More or less equations are the same. And Rayleigh, जो Lord Rayleigh था ना, उसने ये equation दी. So you can basically NA is a numerical aperture, and you can consider that is 1. So just to simplify, this becomes 0.5 times lambda. So that is lambda by 2. Okay, R is the distance between two objects. You can use this equation, which is very close to. So 0.61 is not very far from point. So this is the I will not go into detail here. So now next point is that how the electrons talk to your sample. Let me skip all these things, okay, because we don't have much time. So now let us look at your sample again. So if you have this is your sample, ये वाला तुम्हारा sample है ना? You have your sample. I was discussing it can be a polymer sample or it can be some catalyst. Okay. So if you bombard your sample with this is your high energy beam, what will happen? So when the electrons you bombard electrons on your sample, which is for example titanium oxide, zinc oxide, or alumina, or some polymer, PMMA, polypyrrole, anything. What can happen actually? So these are the processes which are listed out. Let us start one by one. So these electrons can knock out electrons from the valence bands, or basically or any even a little bit interior, and they can knock out electrons, and those electrons becomes secondary electrons. So they are not part of the original beam, but they are part of your sample. So they are very useful. So secondary electrons are used to generate SEM, scanning electron microscopy में यही electrons use होते हैं. It's a very rich technique. Every signal is a technique here. तो कुछ waste नहीं होता है यहाँ पे. ये सारे जो signal देख रहे हो ना, उसमें सारी chemistry information बहुत आती है इसमें, बहुत ज़्यादा. So you get topography information from SEM, which is done by collecting the secondary electron. Okay, next, so these are inelastic electron, right? It's an inelastic process. It's an elastic process. There is an energy transfer. So these high energy electrons will transfer some energy to your sample. When I say some energy, if it transfer all the energy, then your sample will just convert into plasma. You will not see anything. पूरा उसकी हवा बन जाएगी, हवा भी नहीं बनेगी, हवा के भी हवा के जो भी हवा में भी कुछ तो होता है, मॉलिक्यूल्स होते हैं ना, you will not have any even atom नहीं होगा, प्लाज्मा हो जाएगा. Plasma means that all electrons are different, separate, and then you have positively charged nuclei which are separate. So that's a plasma state. You won't have any molecules actually. वो मत नहीं करना है हमें. Unfortunately, it's not possible because scattering cross section of I will not because it's a physics term, but it is very useful. So electron scattering cross section is basically layman language. It is for chemistry students I would like to use layman language. कि भाई कितनी probability है टक्कर की. For example, you are throwing a ball on a glass window. Don't do this experiment. Okay, and if you are throwing a tennis ball on a glass window, and suppose 100 times, 90 times the ball bounces back towards you, okay, with the same velocity. That means it is an elastic interaction. And out of 100 times, 10 times, suppose you break the glass, okay, and then that is an inelastic interaction. You can't break a glass 10 times, perhaps. Before that you will be beaten up probably. So okay, so don't do this experiment. So got it. So the probability, it's a basically probability. So probability is even not that actually. I mean, electron C atom as a very small particle. They don't see atom as as a collection of some electron, proton, neutron. But atom is basically a very fake concept. All of you are aware of that. There is nothing called atom or bond, right? It's our fake imagination. It's just a collection of particles, neutrons, and protons and electrons in an area which we call, like for example, you are sitting in a room, you call it, and your mother is there or your father is there, you are there, you call it as a home, so, right? But you are not home, right? So yeah, so you are okay. So then you can have X-ray emission, which are very useful, which will give you analytical chemistry information. ये कौन सा atom उसमें है? Mosley का याद है ना? I discussed about Mosley. Then you can form electron hole pair here, because some energy is transferred. So from valence band to conduction band, electrons are kicked out, and then those electrons will form. Those electrons which in higher energy states can bounce back to the ground state, and then you can have visible light also. You have a bremsstrahlung X-rays also, which is actually, this is one of the signal which is I don't find much use. Is the only signal. And then you can have direct beam, which is used for all your imaging. जो imaging वगैरह तुम देखते हो, TM images, ये सब इसी से बनती है. बाकी सब तो फालतू है, नहीं फालतू नहीं, बहुत काम के हैं. ये Hardaf and there are many techniques which I cannot tell you in today's course, okay, unless you take a larger course. So I will skip this because it will take long time. Okay, so I'll just give you overview in this class. Considering the time involved. So there are many techniques, as you have seen, based on electron microscopy. Conventional technique, I have already told you that there are two variants of that: bright field and dark field. So bright field bright field technique is basically based on these direct electrons, right? And if you catch diffracted electrons which are back diffracted, if you catch them and make image out of that, then you call it dark field. Okay, these are undiffracted electrons, right? And if you don't want to make image out of the diffracted electrons, and then you just look at the diffraction pattern like you do in X-rays, then you can call it electron diffraction pattern. We call it selected area electron diffraction because you can select the area. That beauty is that you can select the area that हमें मुझे यहाँ से diffraction चाहिए, मुझे यहाँ से नहीं चाहिए, यहाँ से चाहिए, मुझे यहीं का देखना है crystallinity, मुझे इसी में interest है, इसी grain में interest है, ये grain का crystallinity मुझे अलग लग रहा है. So you can select actually that even if the whole particle, your sample is a mixture of polycrystallites. But remember, polycrystalline sample means that each grain is still a crystallite. It's a single crystal. In bulk, you can say that, oh, my sample is not single crystal; it is a polycrystal. But for electron microscopy, you can select one grain which is a single crystal. So you can do in principle single crystal X-ray, single crystal electron diffraction. इट्स नॉट अ जोक. कितना मजेदार चीज हो बता दिया मैंने, ठीक है ना. लोगों को लगता है सिंगल क्रिस्टल बनाने में बहुत बड़ा सिंगल क्रिस्टल चाहिए, उसको माउंट करना पड़ेगा एक्सरे में, ठीक है, और उसको फिर माउंट करना बड़ा मुश्किल है, ग्रो करना. इलेक्ट्रॉन माइक्रोस्कोपी में लाइफ इजी हो गई. इफ यू हैव एनी क्वेश्चन, समबडी, या इफ यू हैव एनी क्वेश्चन अनम्यूट करके और क्वेश्चन पूछ लो. ओके, it will give break to my voice also. Any questions so far? Okay, because I'm not sure whether I'm going too fast or too slow, or for some people it may be too fast, some people it may be too slow, because it depends upon your individual exposure, prior exposure. So it's for a teacher, especially in the online mode, I cannot see you, you cannot see me. So please forgive me for some deficiencies in my teaching. I'm trying my best, and probably you are trying your best. But okay, so I show movies also in real class. Most of the time this class happens in a big room second floor lecture. All of you are aware of that. Some students are new, so they have actually joined NCL, but they have not entered physically inside NCL building. So normally these big classes happen in a large room. So there we show some movies also. So anyway, so movie weekend पर देख लेना है ना YouTube पे. So then you can have I will not teach this because convergent, not today, some other time if you are interested. So high resolution. Now high resolution technique is basically, suppose you have a direct beam and then you have diffracted beam. Then you will have, suppose this is a direct beam and this is Bragg angle and this is diffracted beam. So if you allow both of them, then you can have high resolution DEM. High resolution TM ka मजेदार ये है कि you can see lattice fringes, the rows of atoms. I mean, again, as I told you that you don't see atom, but you call it as an atom actually, because there is nothing as such as an atom. Okay, so then there are this X-ray spectroscopy you can do. We have already discussed most of these things. I'm repeating. Yields you can do, and there are other techniques. In situ TM is becoming very famous for chemists. This is very good for biologists. इसमें Nobel Prize मिला था prior TM पे chemistry का, right? And I'm sure that one Nobel Prize may come in next 1 decade in chemistry in situ TEM, and in the catalysis area it should come. Okay, यार ये सब मत लिखो. Yes. So I don't know what I did. Yeah. So how do I erase this? Okay, institute. यार ऐसे तो मत लिखो, पूछ लो यार, ऐसे मत लिखो. फिर या तो मिटा दो तुम. You please erase this because you are wasting my time. Okay. It will stay here. Yeah. Thank you. Thank you. Thank you. You are nice students. Thank you. So you asked the question, na? Okay. So this institute, I think the students was asking question that what is this for? Institute TEM, मुझे लगता है question इसलिए आया, मैंने Nobel Prize बोल दिया, right? Otherwise question नहीं आता. Institute TEM, I had arranged one lecture at NCL. Many people attended that and they learned it. So Institute TEM is the next thing which is going to be contributing big in chemistry. So here Institute TEM means you are carrying out the reaction inside the sample holder, tiny sample holder of TEM, and you're applying high pressure, high temperature, whatever conditions you want. So you are looking at the formation of matter, inorganic matter, as in the real time actually. That is Institute TEM. Okay, any question? I hope it is satisfied. So you can type your question on the screen also, as long as you raise it. Okay, no problem. You can if you are comfortable with that, I have no problem. You can type. It was a good idea. And thanks for erasing it. Thank you. So now I told you so many things, but now you will be asking who detects it actually. So there are detectors actually. Detectors detect it. So you can see that there are different detectors. So this is basically illumination system, prime illumination lens system. So the electron beam comes here, and then you have different detectors. So this cross is basically magnetic field. This one. They are, sorry. So these are magnets. These are magnets, and as these are all magnets. Okay, ये magnet है. This is the detector for backscattered, electrons. This detector. This is your specimen. You can see this. This is your specimen. This is your specimen, and this is your detector here. This is EDEX detector. This is selected area electron diffraction detector, and yields detector is here. I'm sorry. So, so you have many detectors here, and okay, so let's go forward. And what information you get? So this is the example of manganese oxide nanotube and cerium dope. This is okay. You can see this now. For the chemistry student, the challenge is that you would like to show that yes, there is manganese inside, and where is selenium going actually? Whether selenium is there? Suppose you do the ICP. The problem is that even if selenium particle is there somewhere outside, okay, separate. Selenium has precipitated separately. Or sorry, cerium. Sorry, I'm sorry. Cerium. Cerium is has precipitated separately. So so that then you can not it will give you overall result. So suppose similarly, suppose manganese is you know, has interacted with something else, so then it will give you averaged out information. But here you can pinpoint, you can show that where manganese is there and where your oxygen is there. And so if you have more, so this is basically elemental mapping. You can see, so as I was telling you that you can localize, you can get localized information. So this technique is basically scanning transmission electron microscope. So so how do you do that? Normally, let me use the whiteboard. Yeah. So if you take the so electron beam can come like this, straight parallel beam, and this is your sample. And so this beam, this electron beam can go like this. Primary electrons I'm talking actually, okay, not the secondary electrons or something like that. So then you can collect them and then make image out of these electrons here. And you can also basically you can also let me change the color. I'm being more creative here. Which color you want? Yellow. So you can also have electrons which are diffracting at an angle. Okay, you can have diffraction. You can have diffraction also at other side also, because this it will be a cone actually. Ideally, it will be like a cone, right? But we are showing a two-dimensional picture, very simplified. But ideally, it will be a cone, three-dimensional diffraction. So suppose this is theta. So you can collect these electrons and you can get electron diffraction. Okay. So there will be X-ray generation. So you can collect X-rays. You can do energy dispersive X-ray spectroscopy, right? So even here, what I'm trying to tell you is that even here, suppose you select area of 200 nanometer, you can say that, sir, it's not localized information. You told me that you can get information about single atom, but 200 nanometer is quite a lot, right? So what you can do, instead of using this parallel beam, you can use a beam like this, nano beam. Okay, so electron beam can come like a pen which I'm using for writing, something like that. So again, so electron, you can put a lens here, and okay, and the lens can converge this beam at a very tiny probe size. So depends upon your probe size. So probe size, smaller the probe size can be few angstrom. So now if you put the same sample, now you are getting all the information from this tiny area. So you have to move the beam, right? You have to move the beam here or here. Okay. So then you have to scan the area, this area, this area, this area. So you start getting chemistry information from selectively from. Okay. So this is called STEM. Okay, scanning, transmission, electron microscopy. Transmission means because you are collecting the transmitted electrons. That's why you call it transmission electron microscopy, right? So scanning. So because you're scanning the beam, here you are not scanning the beam actually. Okay, you are just selecting an area, different area. If you have any question, you can ask me here. Unmute yourself, please. Okay, so let me change the share. New share. Yeah. So sorry. Yeah. So you can see this is how this image is generated here. So you can do many things. You can see that I have not taught you this technique, so I will not touch upon this today. But in my other lecture, if you are interested, then you will get more information about HARDAF, because HARDAF is a bit advanced technique. So I can teach you about this image, this one. Okay, this one is basically again high resolution TM image of iron oxide nanoparticle. Okay, and these are coated with oleic acid. Okay, OLAC is basically oleic acid. So you have a problem here that you have a inorganic organic combination. So you have organic a shell and inorganic core. Okay, so you have iron oxide Fe3O4, and here it is written FeXOY. Okay, so you can see that there is a. So how will you know that it is iron oxide? How will you know that this internal part is not oleic acid? How do you know? So there are various ways to know. If you notice, if you zoom this, you will see that there is a self assembly of molecules, oleic acid. Inside you can see there are lattice fringes inside. So inside the particle, you can see there are lattice fringes. Actually, there is some kind of crystallinity. This is one way of knowing. Okay, there are other techniques which I am not discussing. For example, HARDAF is one of the techniques. HARDAF can tell you that there are higher Z contrast. Basically, heavier atoms are sitting in the in the core area. The shell is composed of lighter elements like carbon, oxygen, and okay. So this is how you so you use a combination of techniques to confirm that inside the core is of iron oxide. Of course, you should not try to uh, 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 precisely calculate stoichiometry Fe x and y. So x and y to certain approximation you can calculate, but for stoichiometry, perfect stoichiometry calculation, I would like to suggest that you use EELS or ICP. Still is better for precise. But there are trade-offs, as you know, that ICP is a global technique. I mean, it gives you sampling size is too large. So every technique has got its own problems. So you should be aware of that when you're trying. I'll skip this. Yeah. So this is another example, so that you can do elemental mapping. So what it teaches you is that you can see that this sample, whatever it is, it doesn't matter, but you can see that this is iron, chromium, and titanium. Blue is titanium, blue areas. So you are able to, so this is 100 nanometer. You can see that this entire length is somewhere around only 500 nanometer. So suppose you have a, a sample which you have synthesized, and so you can see that you can show that this area you have more whatever color it is. I really don't know what color it is. I will just call it a red color. Okay. I'm not color blind, but I don't have name for that. So I'll just call. I just call anything similar to this color as red. So all this red color is iron. Okay, rust color, whatever. I have a T-shirt with this color. Okay, so my T-shirt color. Okay, and this green color is basically chromium, and blue dots are all titanium. You can see that a lot of blue dots are there. So you can see that there are concentrated areas where you have more chromium particles. Probably it's chromium oxide in the oxide form, or elemental form, just chromium or titanium. So this technique should not be attempted for oxygen determination for the reasons I cannot disclose you in this lecture. I have to talk in other lecture. So now you can ask the question that, अरे यहाँ तो oxygen ये किया है, you know, here. See, this is basically a new generation of technique where resolution is much better, and EDAX detector is they're much advanced. So here they can afford to show you where oxygen is, but normally it should not be attempted because it's not very good idea. So this is older generation of data. You will not find in older generation you will not find oxygen, but newer generation data you will find oxygen. And this is normal. A TM image looks like this actually. It's also because it's an old image, you will find it very ugly actually. So this is your X-ray spectra. Mosley, Mosley gave us this form equation. So we know that we can associate the energy with the element K alpha, K beta, whatever it is. So there also a lot of problems are there. It's not that easy because there can be overlap between two different elements. So it's a different point of discussion that time lagega. So how do you do if there is an overlap between different peaks? Okay, so you have to be very careful. And there are software tools, and of course there is a overlap. And now I would like you to look at this very carefully. All chemistry students, all physics students, all material students. So look at this is atomic percentage, the y-axis, and x-axis is distance in nanometer. Now you can see that there is a huge amount of error bar, plus minus almost 5% atomic percent in getting the atomic percentage of iron and titanium. Now हमारे स्टूडेंट क्या करते हैं NCL के और सारे स्टूडेंट्स बाहर के भी, they will give the atomic percentage. सर मेरा एटॉमिक आयरन का परसेंटेज है 10.65%, राइट? ओ मैं तो बोलता हूँ तुम्हें तो नोबेल प्राइज मिलना चाहिए, क्यों मिलना चाहिए? बिकॉज यू हैव रियली improved the technique. Like either you have improved the technique or you have not understood it. You can see that this author is generous enough to accept that there is a huge error bar, and indeed there is an error bar. So as I told you that this technique EDAX should be used very carefully because there is a huge amount of error. And why this error is there, that I'll be able to teach in bigger lectures. Okay, if you are interested. So these are the detectors, how the samples are placed. You can see it physically. So this is basically, you can zoom it here. This is typically a TM grid. You can put different TM grid. These are all TM grids here. You can rotate this and you can put, this is inside SEM, scanning electron microscope. Okay, and you can, these are the detectors. This is detector. A different detector you can collect different signals. EELS, as I told you, that EELS is basically electron energy loss spectroscopy. अब ये क्या चीज है? I can use this to explain you that this is your sample again, and you're change the color, and this is your electron beam, and this electron beam, once it hits the sample, so this will eject. So okay, so after it will change some energy. Okay, this is outgoing electron. Suppose this energy was 100 electron volt, and this generated an X-ray of, for example, copper K alpha or whatever, or which has got energy of few 100 electron volt only. I don't remember what is the energy in electron volt. We know that lambda, but I do not remember. If you know that, you can just write here. So suppose it is just to be for the sake of calculation, suppose it is 500 electron volt. So you can see that 100 kilo electron volt minus 500 electron volt. Can you calculate? It's so small. Sorry, 500 electron volt. Just negligible, right? It will be 99.5 electron volt. So that means it is very. It's not easy to. So suppose you have one electron which is of energy 100 kilo electron volt. Another electron is basically 99.5 kilo electron volt. So believe me, it is not very easy to distinguish between these two electrons. That's why yields is a very expensive technique. Okay, so but it is expensive, but it can give you chemistry students will be especially happy because it can not only give you elemental identity but bonding nature and valence band, conduction band, electronic properties, surface property, for example, whether how clean is the surface and all kinds of things. I mean, there are many other techniques like subtle techniques like I told you that hybridization and other things. There are many other like, for example, if you want to know surface plasmons, it can tell you, it can show you many interesting things actually. It is very powerful technique, but I will not go into detail in this lecture. Yeah. So the technique which is and that is not available at NCL also. So the technique which is available and it is widely used by NCL student is this technique. NCL student love this technique, even though many of them they don't understand actually. Without understanding, they allow it actually. It's a problem with all of us. Okay. So let me see. So this is a typical electron diffraction image. Okay, so it looks fairly complex. So you can calculate. So this is basically in the reciprocal lattice space. So that's why I told you first you have to understand a reciprocal lattice. You have to understand first the real lattice, and first then you have to understand. People don't understand even real lattice. Okay, then you have to understand the reciprocal lattice, and then so these dimensions are all inverted in angstrom. Okay, 1 over angstrom or 1 over nanometer. So, so these distances can give you an idea about 1 over d. D is lattice spacing actually. So you can calculate the lattice spacing from each diffraction. So these are all diffraction points actually. This one, and you can see there are other diffraction spots also. This is there because of the sample nature. You can see there are some precipitates in this sample. So this is your sample in the inside. This one. So I'll not go into detail again. So this is another electron diffraction pattern. Okay. So and in larger course, we give them some exercise hands-on on software. So you can install the software, give them some exercise to carry out. So this is selected area electron diffraction from this lanthanum carbonate crystal, and this is the example of. You can see that if you have plate-like texture, or you have a single crystalline, or it is polycrystalline. So this is polycrystalline, this is plate-like texture, and this is crystal. So you can get for single crystal you get clear dot pattern. You can see it here, and this is plate-like texture. You can see this is elongated here. You can see this is elongated here, and here you can see that this is polycrystalline. You can see that here you have these are basically rings actually. You can see that it is forming ring pattern. So what will be the electron diffraction pattern for amorphous sample? Just think about it. Let me know. So there are advantages, disadvantages of every technique. Any question? Guys, girls, any question? Students? Are you understanding it or no? Any question? Please unmute yourself.
No, sir.
No, sir.
No, sir.
अरे बड़े समझदार बच्चे हो यार तुम तो। मुझे तो अभी तक समझ में नहीं आया इलेक्ट्रॉन माइक्रोस्कोपी अच्छे से। हाँ चलो बढ़िया है।
Hello, sir. Hello.
एक भी क्वेश्चन नहीं
I
है?
have one question.
ओके गुड गुड। मुझे तो अभी तक समझ में नहीं आया अच्छी तरह से इलेक्ट्रॉन माइक्रोस्कोपी। साल हो गए मुझे। हाँ बताओ।
Hello, sir. Sir, you tell about the secondary electrons which are generated after that transmission of that sample,
Yes.
means scanning of that sample.
Mm-hmm.
Sir, what are that secondary electrons? How can they generate and how can we amplify that?
Okay. Good question. So remind me in last 15 minutes. Okay. What is your name? What is your good name? आपका नाम क्या है? दोबारा बोलो आपका नाम। हाँ sorry. Okay, so anyway, so this so this I have a separate presentation which I have prepared, and that presentation is on scanning electron microscope. So that students question is related to secondary electrons. So those that I teach separately. I will teach it in probably last 10-15 minutes. ठीक है ना?
Yeah. Yes.
मुझे आप बुला देना लास्ट में ना। आपका नाम क्या है? Sorry.
Swapnali Kirdant.
अच्छा स्वप्नाली ठीक है। Yeah, any other question? So Swapnali's question was related to SEM, so I will answer it later on because I have to open another slide for that. Yes. Any other question?
Hello, sir. I have also one question that you tell about the SAD pattern.
आपका नाम आई तो नहीं होगा? मेरी एक स्टूडेंट थी, उसका नाम था सुनो मेरी एक स्टूडेंट थी, उसका नाम था आई सेल्वा रूपा क्रिस्टलीना।
सर दिस इज स्वप्नाली। सर दिस इज स्वप्नाली। I have another question that you tell about the SAD pattern.
Yes.
Sir, that shows the rings. That picture shows the rings. And sir, how I'm not getting that the SAD pattern.
So okay, so you are not getting how this SAD pattern comes, right?
Yeah.
Okay. Let me explain to you. I think the slides are there. Come to the slide. Yeah, here. So see, so this is your incident team. Okay, this one, and this is your specimen. This one. You use the pen. So this is the specimen, and this okay, Swapnali. So when the electrons they pass through your sample has got some. Just imagine that this is your sample, and there are mirrors, many mirrors like that. So mirrors are basically your lattice plates. So these are basically what you call it, partly polished, partly silvered mirror. So some part of radiation will go straight, some part will get diffracted. So I will not be able to see the chat box. So please don't ask questions in the chat box. Aman has written some question which have more resolution, SEM or TM or Y. So Aman, please, I'm this time I'm looking at the chat box, but okay, so you can ask the question which is easier for me. So so these mirrors will reflect the beam in some direction, right? The mirror can be in any direction. So that's why Bragg's use this term reflection. So we know that it's not reflection, it's diffraction, but for the sake of understanding, you can see that you can basically consider that there is some kind of a mirror. So these are your Bragg diffraction electron, okay, at angle theta. You know that equation is lambda is equal to 2d sine theta, right? So now you have got these electrons. So you can collect these straight electrons which are coming straight here, so this will form your central point which we saw, right? जो बीच वाला जो डॉट है, ये आपका साइड वाला डॉट, ये एक हर पॉइंट एक डॉट बन गया. समझ में आ गया सुखमाली? If you basically take an image here, so every beam which is basically focusing somewhere here, they will become dot, na? समझ में आ गया ना? So basically these electrons are carrying information about the d values of these planes, okay, the d values, okay, through this equation, because you know the theta, we already know lambda, so we will know d. So simple. So these are basically these dots. So you can make image out of that. This is described here, but it is in detail. It is described here. Selected area electron diffraction. So you can see that this is a central dot. See, this is Swapnali, this is a very complex technique. So you have to, this is not possible for me in this lecture to explain you in detail. But these are the electrons which form selected area electron diffraction, right? Let me go back. Any other question? Any other question? So you can see, Swapnali, that I was showing you that this is a central dot. जो सीधे जो इलेक्ट्रॉन्स आए जो बिना डिफ्रैक्ट हुए वो यहाँ पे आके जमा हो गए, है ना? जो डिफ्रैक्टेड हो गए, ये डिफ्रैक्टेड इलेक्ट्रॉन्स हैं सारे, वो यहाँ पे आ गए. सेम जैसे लोवे पैटर्न होता है ना, लोवे पैटर्न वो सेम ही है, कोई बहुत ज्यादा कॉम्प्लिकेटेड नहीं है इलेक्ट्रॉन डिफ्रैक्शन. Actually, if you understand it that way, it's very simple. Actually, it's not a complex technique. Actually, any other question? Thank you, Sapnali, for asking question. Bolo. Anybody else? So, I will take another question which was there in the chat box. Let me see the chat box question again. So, Aman Kumar asked me this question that which will have more resolution, SEM or TEM, and why? See, you cannot directly compare the resolution of SEM. So, can we compare the SEM resolution and TEM resolution? So these are very different technique actually. So one technique is in SEM, basically you bombard this with electrons and then you collect secondary electrons here. Okay. So it's a very complex process because these electrons, if you zoom, these primary electrons will generate, they will spread out in a large area here and they will generate secondary electrons. So basically secondary electrons, if I give you simple answer, secondary electron SEM has a lower resolution, much lower resolution, much lower resolution, but and TEM can give you resolution down to 0.35, 0.4, let's say half of the angstrom. So SEM resolution depends upon, because SEM is basically you have to converge the beam, so it depends upon how small beam you can make. But I normally do not, nobody in electron microscopy compare these two techniques, because these two techniques are very different. I mean, you don't use these techniques normally on the same sample, because SEM is mostly for the samples which are not possible. You cannot put in TEM unless you don't have TEM. If you can use TEM, you would like to use TEM on the sample. Suppose sample does not limit you. अगर आपका sample बहुत thick है ना, तो अच्छा, आप SEM में कौन से सैंपल डालोगे? SEM में मोस्टली सैंपल वो डालोगे जिसके बहुत थिक हैं, आप उनको थिन नहीं कर सकते हो। एंड TEM में क्या है कि आपको थिन सैंपल डालने पड़ेंगे, जो यहाँ पे लिमिटेशन दिखाई गई है। So sample must be electron transparent. This is for TEM. Okay. This is also technique for this is also limitation for HRTEM, that you should take thin sample. But this is not the problem for SEM. So SEM is basically very powerful technique for biological sample, polymer, thick polymer. So thick sample. Okay, you can put entire basically hamburger there inside SEM. So we will take some questions now, and then I will open SEM slide because SEM presentation, because I promised that. So sample preparation is very time consuming in TEM. In SEM it is not. SEM's sample preparation is rather easy. You have to just coat some thin metallic layer for electron conduction, and you're all set. Here you need quite a bit of sample preparation. You should know the concentration of the particle, otherwise you will not get what you are looking for. Samples are vulnerable for radiation damage because the beam energy is very high. I told you. Magnetic materials will find life difficult because if the magnetic field is very strong, so then that's going to be the problem. There are many advantages also, many advantages. Because of lack of time, I will not be able to go. What I will do now, I will just give you a brief summary of the techniques which are possible. So you can see that these are the different kinds of electron microscope, and this is one of the highest resolution microscope, which it was. Now you have even better microscopes. So you can see basically what you can see is a graphene layer, single layer, double layer. You can see atoms. You can see atoms migrating from this point to this point. Actually, you can see it here that these electrons have migrated to that place. Because of what? क्योंकि वो इलेक्ट्रॉन की एनर्जी की वजह से these electrons which are sp2 bonded, basically you are breaking those covalent bonds. The energy is so high, and you are making new bonds actually here. So it's very powerful technique, and I can keep on teaching you. I would love to teach you, but there is not much time. I will now focus on another technique. Okay. Let me get. Yeah. So this is my next presentation. So here I will be teaching you some slides. This entire lecture can take up to 2 classes, around 3 hours. And I think if you're interested in past lectures, those recordings, some recordings are available on YouTube. Okay, so you can look at past teachings. Fortunately, we did this online teaching, and many of those lectures are still recorded and available on YouTube. So this is the difference between TEM and SEM, and I will just tell you what you're looking for. So we can put all kinds of samples. Okay, we can put bhakri and bhaji. You can put everything. You want to know the microstructure of butterfly or cockroach, bring them on, bring everything. Okay, don't worry about that. Okay, we can measure all of everything. So this is Chinese soldier. Okay, terracotta army soldier. So how does it work actually? Let us look at that. So basic principle remains, basic physics remains the same. There is no change in the basic physics actually. How electrons interact with the atom, it is the same as what we discussed earlier. So let's keep all these things. Yeah. So this guy called this guy Aman, or I don't know. So his question is answered here. So, so high resolution field emission. So there are two kinds of emission by which you can emit electrons: field emission and thermionic emission. Right? Field emission is basically you apply electric field and then you pull out the electrons. And thermionic emission basically you heat the filament, and if you heat the filament, then you can take the electrons out. So field emission, where you take out the electrons by applying electric field, that is preferred over thermionic emission because of several reasons. Because of energy spread is much less. I mean, the electron beam is more monochromatic, and if it is monochromatic, then there is less chromatic aberration in that. So you can see the images much clearly. So you can see that the resolution has gone down to almost 5 angstrom. Okay, so as I told you, I hate to compare both techniques because normally this is again I'm telling you I would not compare, because this technique is very powerful SEM, and no uh, 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 it doesn't matter what is the resolution, because even when the resolution was very bad for SEM, it has contributed too much to the sciences, biological sciences, too much. I mean, I cannot just tell you. So beautiful technique actually, SEM, so beautiful technique. And um, so I think I may have some images, but so there are different kinds of electron guns. I told you that you can take tungsten, you can take lanthanum hexaboride here, and you can take field emission gun here. So different kinds of guns are there. So this is your electron source. You can see this is a filament here. Okay. So you heat this, and by Joule heating, you start getting a beam of electrons. And in the field emission, you get um, electrons which are pulled out by field, applying field. So then you have this lens system, you have the condenser lens C1, C2, and then you have this deflection coil, because you have to deflect it basically. You have to scan the beam here, raster scan it. Remember, it is SEM. So then this is your specimen, this is your cockroach or sandwich or whatever, or bhakri. You can put anything actually. I'm not kidding actually. Even in this NCL101, you can put a piece of bread there, and you can look at the, or you can put butterfly wing if you want to know what causes the, or peacock feather. You can put a peacock feather. I would like to tell you one interesting science. See, what is it? You might have wondered that crows, house crows, they are very dark in the color, right? बहुत ज़्यादा dark हैं. So scientists always wanted to create darkest material which can absorb almost all the visible light in the laboratory. And believe me, it is an effort. And in nature, you find that crows are so dark. So what is it is not melanin, or it is not some pigment, especially in crows. Different the science is different for different species. So So when you put the so this crow feather in scanning electron microscope, you can look at the microstructure of crow feather, and there is a very interesting photonics of those the way the microstructures are organized. So that leads to the maximum absorption of light by uh, crows. So that gives them such a dark color, actually shiny dark color. So SEM has, as I told you, contributed in tremendous science. So similar to and another thing, that because there is a lot of space inside SEM, so you can put a lot many detectors which are not possible in TEM. TEM में इतना space नहीं होता है अंदर, है ना? TEM बहुत special technique है. So you can put many detectors here. Of course, you can put EDS. You can EDS. You can do. You cannot do different diffraction here, but you can do diffraction. It's possible, but I will not go into detail. So so resolution depends upon spot size. Okay, so smaller spot size, better detection. So I'll not go into complexities because it's not the right platform. But you can see that these are different detectors: Everett Thorney, second electron detector. This is backscatter detector. This one is backscatter detector. This is a vacuum gauge, and this is for this is your EDS detector made by Oxford Instruments, and this is magnetic pole piece, and this is the main detector for second electron. This is called Everett Thorney. There are two detectors. One is in-lens detector, and another is Everett Thorney, and yeah, this is in-lens detector actually. Yeah. So it's very powerful for chemistry because this for a catalysis student or some material science student, I mean, this detector will be very useful because it can distinguish even work function of the electron. So I think I will end it here because there is no end. I can keep on teaching. So you can see there are some of the SEM images. If you are curious how the SEM images look like, you can see that you can immediately distinguish that they are more lifelike actually, right? बहुत ऐसा लगता है कि एकदम लाइफ लाइक है, मतलब एक्चुअल लाइफ टाइप के लिखते हैं. ये देखो एक I'll just show you some images. You can see this. This is an SEM image. This is an SEM image. These are all SEM images. You can see image of a beetle. I told you, right? You can do. You can image many things. How beautiful the beetle is, and you can see as a chemistry student or as engineer, you will be very interested. In fact, it's a physics topic, but if you just look at this structure, it looks like some beautiful sensor, right? Such a nice periodicity is there. So you can see it's very useful. It's useful for their survival of the beetle. They are very powerful sensors actually. We don't. हमारे पास नहीं है उस सेट के सेंसर. तुम्हारे पास मेरे पास नहीं है. इनके पास बहुत ज्यादा है. हम लोग तो एकदम गए बीते हैं. हम लोगों के पास हम एक माइंड लेके घूमते हैं, बस वही है. बाकी हमारे पास सेंसर सब खत्म हो गए. So they don't have a conscious mind, but they are very powerful sensors. Believe me, their survival instinct is much better than our survival instinct. You can see a lot of beautiful structures here, right? And वो स्टूडेंट का क्वेश्चन इसमें आंसर्ड है. अब मैं इतना डिटेल में जाते हुए मैं दिखा सकता हूँ. स्पेशल रेजोल्यूशन ऑफ SEM, राइट? बहुत डिटेल में है चीजें यार, बहुत डिटेल में है, तो इतना पॉसिबल नहीं है. इसका कोई सिंपल आंसर नहीं है, ठीक है ना? इसलिए मैं एक्चुअली दैट see how beautiful it is. You can see titanium wires twisted pair around another nickel wire. So ये nickel wire है, बड़ा ये वाला, ठीक है? ये nickel wire है, ये टाइटेनियम का वायर है ये ऊपर. You can see what it is shown here, that here you can see to distinguish in some of the images. This is backscatter mode. Backscatter mode, you can see slightly the contrast difference. okay, between this and this, because there are two different elements. That's why you can see the contrast difference. And this is the secondary electron image, which does not show you, which does not have exact contrast. So you cannot distinguish between this element and this element, between titanium and nickel. But it's a beautiful example. Titanium kahan aata hai? Titanium and nickel. Okay, so nickel has the Z is basically 28 and titanium is 22. So you can see this is a slightly heavier, atom. You can see it's darkish than this. So this is the beauty. You can distinguish between neighboring elements. They're quite neighbor actually. They're not very far actually. So yes. So with this, I end today's class. And if you have any question, I'll stop sharing. And I open my.
Hello.
Yes.
Yes, sir. So as you said that one can scan any object through this SEM, like burger or anything. So
Yes.
is it possible to get the compositional and crystallographic information at the same time?
Composition, yes, composition you can get at the same time. Crystallography you cannot get with SEM. That's the problem. You can get in backscatter mode, but the detector is not available at NCL. I met